How is everybody this morning? Hopefully everybody's doing okay. I know in my part of the world it's a beautiful, bright, sunny morning in May. I'm hopefully looking forward to being able to get out into the garden a little bit, digging around. I was in a wholesale club buying a gigantic bag of spaghetti because that's my life now. And I noticed that they had a one of those sort of three-sided display racks of all things seeds, vegetable seeds. And I was like, gosh darn it, that's a thing you can't really get at the moment. For those of you who are not living in Ontario at the moment, they've locked things down pretty hard, and it's difficult to. You can't just walk into a store and buy carrot seeds anymore. But I managed to pick up some carrot seeds. I have just enough space in my garden for about 4 or 5 rows of carrots. The carrots did really well in that plot last year, so I'm hoping the carrots do well again this year. I just need an opportunity to stick them seeds in the ground. And I'm hoping today might be the day for it. It looks like it'll be a nice day, so yeah. The peas are doing really well. The radishes are also doing very well. The beets are sort of a bit slow on the uptake, but beets are always a bit slow on the uptake. That's okay. I actually grow the beets mostly for the greens rather than the beets themselves. All right, my image is frozen once again. Trying this again. 1, 2, 3. Bang, bang, boom. All right. I think that we can safely proceed to our lecture for today. Good morning, good morning, good morning, good morning, good morning, good morning, good morning. Good morning to everybody who is saying good morning in the chat. Lovely, 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 lovely. We're going to have a lovely time today. We're going to be talking about statements. We're going to finish off our material on for loops, and then we will be proceeding immediately into structured data types. Structured data types, we're going to be doing basically an elaboration of a lot of the themes we've been developing with tuples and strings so far. We're going to throw that into more general terms. How do you comment chunks of code in Python? Now there is a question that a developer would have. So let me just pull up something that has a chunk of code. Topic 1, sure. .py. So multi-line comments are a thing that Python decided it didn't need. Sort of. However, I believe you can get away with it with triple quote. Now, technically, this is a doc string. This is technically not a comment. You can see comments are done out in gray in this particular editor. However, it sort of functions the same way as you might use a multi-line comment. Yeah. As Mark points out. We'll get into doc strings a little bit. As I said, they sort of they serve a couple of purposes. Uh-oh, my chat is disconnected. Is my stream disconnected? Is everything disconnected, or is it just the chat? I'm frozen again. That seems to be happening quite a lot. Not sure why. There we go. Cool. Let me see. Popping it out and popping it in sometimes fixes that. Yeah. There we go. Oh. There we go. So, let's just get right into it, shall we? So yesterday, we were talking about for loops. We were also talking about linear search. Remember, Linear search is the most basic type of search, where you just search, you just compare everything in a collection to the thing you're looking for, and if you find it, the search was successful. We were going through the differences between doing this with while loops and break statements, and doing it with a for loop. The difference between returning immediately and then returning, holding your return statement for the end. Makes it slightly more readable, but, you know, also introduces redundant statements in your execution. Inevitably. So let's so we were just about to get into like the last 4 slides here, so let's pick the things up from there. So you guys remember, hopefully, the factorial example that we were doing last time in class. Factorial is, of course, the product of every number, every natural number up to n, where n is some natural number, with the exclusion of 0. So this is what we would call an inductive or a recursive definition, because we are defining n factorial using the factorial operation itself. We're going to see how this lends itself to a particular type of program construction known as recursion, but not for a couple of topics yet. We're going to be covering that. I don't know. Is next week Victoria Day weekend? I think it is. I should check this before we go much further. I need to see if next weekend we got the Monday. If next week Monday we have it off, that would be an important thing to know. Nope. Okay. Nope. Not at all. It's yeah, May 24th. Oh yeah. So May 24th weekend. Yeah, actually has May 24th in it this time. Okay, so Victoria Day is on May 24th, so we will have no classes on the 24th, but next week we will cover functions and recursion and numerical computation. We will also have our first test, our midterm test, in the week of May 23rd, on the Saturday. Organization. So anyway, talking about factorial. If you remember our factorial implementation that we were doing. Get it, topic 3.py. There we go. There we go. So this was our implementation of factorial using while loops. Now that we have access to the for loop structure, which is so much better than while loops, doesn't even bear comparison, and now that we have access to the range object, whereby we can generate a gigantic data structure of sequential numbers, it may be that we can, we can use our new knowledge to create a more useful and compact implementation of the factorial function. So, fact4. Sure, why not? So, fundamentally, if you remember, for loops allow you to avoid having to explicitly designate a counter variable, because the for loop itself will it'll take care of that function of counting through a data structure. So we don't need I. However, we still do need the accumulator. We still need some variable that holds the running product of all of these numbers. So we will call that prod. We started off at 1. For x in range from 1 to n, we simply multiply product by whatever x is. And then at the end, we return the product. Come on, man. Can't start losing Using your voice 10 minutes in, that's just terrible. Oh no. Please don't let me have the hiccups. Okay, I think I've conquered them for now. I once gave a lecture, a 3-hour lecture, where the entire final hour of it I had the hiccups. And man, it was not pleasant. Not for me or anyone involved. Doop. Cool. Right. So, if we change our factorial for the one that we just wrote, and then execute this bad boy, Python 3 topic 3.py, bing bang boom, x is not defined. Is it not? Oh, yeah, not there. We'll call it 6. Scrolling up to where we are. This seems incorrect. I'm going to use that multi-line comment thing to just comment out the whole rest of the file. 120. That doesn't seem correct. So let's... Oh, yeah. Because remember... actually, okay. Let's use a print statement to debug this. So, we know that the answer that we should be getting there is 720, not 120. So let's expose what x is through all of these iterations, and then hopefully that'll expose where the problem is. This is a little bit of live debugging. So it goes through 1, 2, 3, 4, 5. 6 is missing. So, if you remember, the range object generates numbers from this one to 1 minus that one. So in order to get to actually n, you have to do n plus 1. That'll give you the correct answer. You can always check what the range object produces by opening up your Python Python 3 interpreter and simply list converting it so that you can actually see what the elements are. Ta-da! Very useful. You can also do this kind of stuff in Python Tutor, which I highly recommend. So yeah, see if there are any questions. Am I frozen again? Jeez. There we go. I wish I knew what was causing that. Maybe I'll actually put some effort into debugging that today. So, here are some common errors that you may experience while trying to write loops. If you're inexperienced at programming, you'll probably even make multiple of these errors at one time while writing one loop. So, incorrect initialization, particularly that of the accumulators. So going back to our factorial example, if I had decided to initialize the product here to 0, I would, there we go, I would get 0 as the result every time, because of course, you know, if you're trying to have a running product, if it starts at 0, everything multiplied by 0 is 0, so you're not actually accumulating anything, you're just gobbling up everything that you throw at it. So that would be an error. Incorrect termination condition of the loop. For example, using greater than instead of greater than or equal to. I would classify getting the range on a for loop incorrect, getting that off by 1. That I would class that in the same in this category of incorrect loop termination. It's akin mistaking a greater than or a less than for a less than equals, something like that. Infinite loops are a common error, more common than you might think. They're certainly a much more pernicious problem when it comes to while loops than for loops. For loops are designed explicitly to try to minimize the occurrence of infinite loops, because infinite loops are such a problem. Infinite loops, of course, occur when the state that you're using to guard the loop execution, the loop condition itself, the variables that are being used to evaluate the loop condition are not changing. Normally, this is because you forgot to, add 1 to the index every time you run through. Just forget that one line of code, and you've got an infinite loop. And as I've said a few times before, computers are pretty stupid. So rather than recognize that they're in an infinite loop, typically what they'll do is they'll just try to run it. They'll run it forever because they have no idea. They can't look ahead in the code and say, "Oh, that's stupid. That won't work. I'm not going to do that." Like a person would, If you told a person, "Okay, you're in a car. I want you to drive at 30 miles an hour for 1 hour, and that if the route that you were driving over happened to go off of a cliff," the person would say, "Well, I'm not doing that. That's stupid. I can clearly see that if I follow those instructions, I will drive my car off of a cliff and die." A computer will just do it, even if the car would go off of a cliff and plunge into a ravine and explode in a giant fireball. The computer will do it anyway because it doesn't recognize things like cliff or danger unless you have explicitly taught it to avoid cliffs, basically. That analogy holds. Index calculations being off by 1. So the error that we had with the range object being off by 1 here, it's kind of, I would say it's sort of, these two are akin, these two are like related issues. So if you get the incorrect condition here, that may result in, for example, not testing the last element in a data collection, or testing one more element in the data collection than exists. These are also commonly known as off by 1 errors. Also, improper bracketing or indentation of nested structures. So, that's a thing that can be, difficult for a first-time Python user to pick up. I actually had a student sending me an email about a problem that he was having with code, where basically he'd done something like this, right? So, and there was a return statement. Let me do it a little more explicitly. It was like we had def some function, and the way that this code had been written was like this. Return whatever. So the error that this person was getting was improper indentation, which is correct, but it was ascribing it to this line with the return statement, right? So in Python, you don't actually have to have a return statement inside of a function. If you don't have a return statement inside of a function, the function will return a special none value. You're also, the other thing is, the statements that exist in the main execution look exactly like the ones that occur inside of functions. There's no real distinction drawn between them, so it's easy to make this kind of error with the wrong indentation level. But this is how Python would interpret the situation. The only statement that's actually contained within this function is A, because that is the only statement that is continuously at level 1 indentation. because these are at level 0 indentation, that tells Python that they are in main execution rather than inside of the function f. Because, of course, it's not sufficient that everything be at the correct level of indentation. It's also a requirement that you don't have a lower level of indentation between. So this was the entire function definition according to Python. And so when you hit this return statement, this level of indentation doesn't make any sense to Python, because it's like, what does this pertain to? I don't have a loop here. If there was a loop here or an if statement there, then that would make sense to Python. But because it's just kind of floating in space, that's an indentation error. So the remedy was to correct the indentation in these middle bits, and then everything was hunky-dory. That's one thing that's important to note about Python programming and programming in general. The line of code that the error refers to is not necessarily the line of code on which the actual error occurred. So, if we fill this up with some sort of, facile code, I just want to show you what the error looks like. Right, so you get an indentation error on line 16. Line 16, right? The actual underlying problem occurs on the 2 lines above that, right? So normally, if you can't find the error on the line that the error itself is indicating, a good heuristic is to look at the line immediately before that, or at least whatever line before that had something on it. Like this, if there were blank space here, then of course you'd still be looking at lines 14 and 15. So yeah, and I guess the other thing that I don't know if anybody said this explicitly yet, but when you get an error, if you actually read the error that you're given, it'll tell you what line the error occurred on, and that is extremely important. It's also possible when you're in the Jupyter, notebook system, to enable line numbers. I believe if you go View, Toggle Line Numbers, there you get the line numbers displayed for you explicitly, so you don't have to guess what line what line is what number. It'll just tell you, which is extremely useful. You'll notice that when I'm programming in my little get it program here, I always have the line numbers displayed. It's like that's kind of one of those little things that a programmer will always have. If you're programming and the line numbers aren't there, enable them. Find out how to enable them and continue on. That's like, if you were doing carpentry, you wouldn't start working if you didn't have a pencil to be able to mark wood. This is kind of the same thing. So, cool. Am I frozen again? Oh, Jesus. All right. So, good. So, here is, I think we'll actually do this quiz as a quiz. A little quiz. This is a function to count the frequency of the occurrences of the letter N in a sequence. Like, for example, a string. This program has some bugs. How many bugs are there, and what bugs can you see? I will leave this up. I will leave this up here, and I will take a look at the chat. And if you can spot the bugs, let me know. Oh, this is actually not a bad This is not a bad thing. I might actually just leave the chat like that. That's pretty good. Hey! Oh, gosh. Terrible. Terrible camera problems today, and they're all of my own making. Yeah, I'm balancing this thing on, like, a book at the back of my desk, so... There. Right. Yes, of course TAs are banned from answering. Okay. So, we've got one. X is not defined. That's correct. So, with this line here, this is going to cause a problem. This will cause a problem as well. Both of these lines are potential problems because X, which is hypothetically our accumulator variable, see it's being used as an accumulator variable, that X has not been assigned anywhere. People who think there are two errors should indicate the second one. So, because X hasn't been initialized up here to whatever the appropriate initialization value would be for X, in this case it would be 0, when we get to this line, assuming we ever run into an N, what is X, what is undefined plus 1? It's still undefined, right? So that would cause a problem. Similarly, if we tried to return the value of something that has not been defined, that's similarly a problem, right? So both of those lines would crap out. So we have another observation. It has a less than or equal to instead of a less than. That's right. So length, remember, that tells you what the size of the string is, right? So if we have the length of potatoes, the length is 8, right? However, if you try to access, let's say X is equal to potatoes, length of X is 8. If you try to access X at the length of X, you will run into an index error. String index is out of range because, of course, the final element of the string is the length of that data structure subtract 1, right? Because it's 0 indexed. We start numbering at 0. So this will be a problem. This means that the loop will run until it hits something outside of the range of the string, and therefore it will fail. Cool. And we have infinite loop because of indentation. Very, very correct. So this guy right here is inside of the if statement. Rather, it's at the level of the if statement rather than at the level of the loop. So this is what would happen. If the first element of... So if we're going through this algorithm from the top, you know, I is 0, while I is less than the length of the sequence. If the sequence at I is equal to n, so if the first element of the sequence is n, then we add 1 to x, and we add 1 to I. Notice there's no else case. If this condition is not true, then I does not have 1 added to it. So, in effect, that means that this algorithm can, assuming we fixed the other errors, this algorithm can only terminate in the case where every element of the string is n. Because only in, if you hit a single element of the string that's not n, then you won't increment I, which means that you won't move to the next element, which means you'll be stuck on the same element forever. So that means that there'll be an infinite loop, as your esteemed colleague points out. So, can I explain again why you shouldn't use less than or equals? There's nothing wrong with the less than or equals operator, right? It's just, well, let me show you. Let me actually show you, eh? Let me, it would be so nice if I could copy stuff from the slides and have the indentation come out, okay? So, let's just fix the other errors and deal explicitly with the loop condition. So, print I. I is equal to I, print sequence at I is equal to sequence at I. Then count n Albania with a capital A. Sure. Oh, yeah, I gotta delete that stuff at the top where I was demonstrating dumb stuff. Return outside function. Is that true? Did I? Yes, I screwed that up. There we go. Sure. So, on the first iteration of the loop, I is 0, right? And we have A. As we increase I through the iterations of the loop, it goes 0, 1, 2, 3, 4, 5, 6, 7, right? And A, L, B, A, and I, A. However, if we try to access the 7th element of the string Albania, Albania does not have, although it has 7 things in it, the index of the final thing in it is 6, not 7. So when we try to access the 7th element, we get an index out of range error, which terminates execution, cuts it short, dead in the water. So that's because we are not stopping soon enough. When we remove the equals to from less than equals to, what we are effectively doing is we are, I gotta actually save that. What we're doing is we are stopping this guy before it reaches the actual length. So if you have the equals in there, this will run one more time when I is exactly equal to the length of the sequence, which is an invalid number for addressing. So if you want to make it valid, you have to remove the equal sign. The alternative to that would be to subtract 1 from the length in the expression itself, and you get the same effect. So, it's like the less than or equal to operator itself is not evil, right? It just, there's no operation which is inherently bad. It's just if you use it in a particular situation and you don't take into account, for example, the size of the, the actual physical size of the data structure you're operating over, you will run into trouble, and that trouble is called an index error. Hopefully that's a decent explanation. Cool. So, yes. So we had three errors there. And just to summarize, for loops versus while loops. For loops automatically initialize and increment the loop variable, thus avoiding certain classes of errors. For loops may necessitate jumps out of the loop by return or break statements, thus having multiple exit conditions. While loops allow a single exit condition and make the termination condition explicit. This is, yeah, sure. For this reason, we avoid break and prefer a single return at the end of a function. Although in this class, stylistic considerations are secondary to functional considerations. So if you get the computer to do what you want it to, that is the primary consideration. Again, stylistic. I would consider this a stylistic consideration. Stylistic considerations are secondary. So there we go. Topic 3. Are there any questions about topic 3 before we move on to topic 4? For the 30 of you that are listening. It's kind of funny. We had 70, then we had 50, now we've got 30. So by the middle of next week, we should have 2 people watching. Okay? Oh, I just closed the wrong one. Oh, man. I'm not actually doing a break. I'm just opening up a folder. I just, you know, call me paranoid, but I just don't want to show the contents of my download folder to the internet. No questions? Okay. So, cool. We'll get a little bit into this, and then we'll have our first break for this morning. We're making good time. So, let's talk about structured data types. So, up to this point in the course, you should have a reasonable conception of what a data type is. We've been talking about data types. Remember your elementary data types: integers, floats, bools, and characters technically, but they hide them, so, you know. What we're going to talk about in more detail in topic 4 are collection types or composite types. So, essentially, the only difference between something like a tuple or a list and a variable is well, let me motivate these for a moment. Let me open up a new topic. Get it? Topic 4.py. So, you may be in a situation sometime where you need a sequence of variables, right? So, let's say you needed like 5 different variables, right, to do various things. And you ended up calling them x1 equals something, x2 equals something else, x3 equals something else, you know, all on the way down to like x20. And, you know, if you're working on actual real problems, these are the types of situations that you run into. Rather than doing that, we are provided as programmers with a shorthand for that. We simply create a list object that has 20 things in it, and then rather than embedding the number directly in the name of the variable itself, you can access it using the indexing operation. There's much more complicated stuff going on inside of this if you start getting into pointers and memory management and that kind of C-level stuff. But for our purposes, you can think of these data structures as being a way of doing things more conveniently. Because remember my mantra. Everything can be done with if statements and while loops. Everything else is for convenience. So let's learn some conveniences. So we've already basically covered in this course tuples and strings. We're going to discuss 3 additional types of data structures, and we're going to use them for some problem solving. You will notice that as we basically once you hit assignment 3, pretty much all of the questions that you will ever do in this course require you to use data structures in some form or another, usually lists. As you're going to see, lists are kind of the go-to data structure for most general purpose applications. So, let's talk lists. Lists are very, 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 very similar to tuples in many respects. The only difference is that they're mutable rather than immutable. So lists are tuples, like tuples, they are ordered collections. The elements do not have to be of the same type, and elements can occur multiple times. So lists, unlike tuples, are designated by square brackets. That's the main thing that you need. That's one of the main things that you need to pick up from all of this business that we've been doing about data structures. Recognize the difference between different bracket types. Round brackets are tuples, square brackets are lists, curly braces are dictionaries and sets, and quotes are strings. That's like important cheat sheet stuff. So if we have a list, 1, 2, 3, 4, potato, we access the elements of it in the same way as a tuple or a string. The only difference, well, one of the main differences, is with a list, if we wanted to assign to one of the elements of the list, we can actually do that, and we can assign it anything, including other data structures, strings, anything you like. So, ham and eggs. There you go. It actually gets replaced. No problemo. So you might already see why lists are in general preferred to tuples for most, like as your go-to general purpose data collection. So again, lists use square braces, whereas tuples use round braces. And probably, this is, programming context is probably the only time you will ever hear parentheses referred to as round braces. But, yeah. So, let's see. Questions. When would you use a tuple over a list? When efficiency is key. So, this is kind of stepping on the slides, stepping ahead in the slides a little bit, but I'll describe it now. So, right now, for you guys, since you're just learning the basics, efficiency is, like, not a primary concern for you guys, right? As I've said multiple times already, getting stuff to work is more important than getting it to work efficiently, right? If you can't get it to work, then there's no point in trying for efficiency, basically. However, there may very well come a time when you actually do need to write efficient programs. So, this business, where you can assign to the elements of a list, that introduces a number of complications that exist at the level of the Python interpreter. So you remember me saying when we were talking about high-level languages, how high-level languages do a lot of work in the back end to make things simpler for you. This is one of those cases. So let's think about, in this example that we just did, we just replaced an integer with a string, right? An integer is the size of one number, right? In basic terms. It's difficult to talk about without introducing the idea that all of these numbers have some underlying space and memory that's allocated to them, right? We've talked about the box model of memory, where, a variable is a box and you put something into the box, and that, that's how variables work, is you put stuff into boxes and stuff falls out of the bottom, right? So when the box is created, it is created with a space capacity, right? So if you create a regular integer, normally, a regular integer has a sort of nominal box capacity of 32 or 64 bits, depending on, what language you're using, etc. A string is larger because each character in a string corresponds to 8 bits, or upwards of 8 bits, probably more like 16 bits. If it's 16 bits, 4 characters are the size of one integer. So you can't fit a string into an integer's box. It's not physically possible. At a certain point, you run into the hardware limitation. Software is sort of flexible and loosey-goosey, but hardware is hardware. It's hard. There are hard constraints. The variable cannot accommodate something that's larger than the number of bits it was created with in normal programming sort of situations. What Python does, in order to allow you to throw a string in where an integer was, throw a string into an integer's box, is it's constantly looking at the box sizes when you make these assignment statements, and it's predicting, or it's not predicting, it's measuring the thing you're trying to put into the box to see if it's bigger than the box. And if it is bigger than the box, it essentially deletes all that and moves it to another segment of memory where it can allocate more space to that box, right? So it makes the box bigger to be able to put the string in it, right? And it does all of this without you ever having to know about it, right? It does all of this behind the scenes. So although it's doing it behind the scenes, it's still doing it, right? And all of these memory operations cost time and resources. So the difference between a tuple and a list is that because you can't assign to a tuple after it's been created, the size of the boxes never changes, so it never needs to be moved in memory. And of course, the amount of time it takes to move something in memory is proportional to the size of the thing, right? It takes, virtually no time at all to move 4 items, but to move 40 million items, that would take much more time, right? So that's the basic idea, is although dynamic memory allocation, dynamic mutable data structures are more convenient for you and I to use as human beings. They allow a greater degree of mathematical abstraction. They allow us to get further away from the hardware level. You pay for it. You pay for it in efficiency. And that can actually accumulate to the point where, efficiency can matter. It does manifest. So that's That's why you would ever use a tuple. Also because it says to use a tuple on a test. That would be another reason. Cool. Also, just so you guys know, you can freely convert between tuples and lists using tuple and list. The words as functions. That performs the type conversion in the same way that you can go between floats and integers. So that's a useful and important thing to know. Cool. Well, I managed to get us all the way to 1020 off of one slide, so shall we pick this up again in 10 minutes? He asks the question knowing that he's just going to do it. Oh my god. Cool. All right. See you guys in 10 minutes. Just trying to figure out this camera business. Testing, testing. Hello! Welcome back. So I think I may have done something about the stupid camera freezing all the time. I looked it up, and apparently this is a thing that's liable to happen if the internal USB hub configuration is overloaded, apparently. So what I've done is I've switched my camera to the USB 3.0 port on my laptop, and my microphone, which hypothetically has a lower amount of data throughput, to the USB 2.0, which is also connected to the mouse. So maybe it was my own stupidity this whole time. But yeah, maybe. We'll see. Hopefully. All right. Cool. So, anyway, continuing on with our discussion of lists. So, if you want to create a list, it's very similar to creating a tuple. You just make one. Bunch of things separated by commas, delimited by square braces. Now, it turns out that it's actually also a really useful thing to have a quote-unquote empty list. Empty lists are denoted by just the two braces with nothing in between. Sometimes, when you're writing a programming problem, the accumulator that you want to create is in fact a list. Like, for example, if you were doing something like the Fibonacci sequence, and you wanted to generate the actual sequence, you would, one way of going about that would be to have a list that would, that you would keep a running list that would have all of the Fibonacci numbers that you were trying to generate, and then you could refer back to it to find out what the next ones were. That would be one way of approaching that problem. So it's useful to start off with an empty list and add stuff to it as you go. So like x is equal to an empty list, x plus equals 1, x plus equals 2, x plus equals 3. You then get x as 1, 2, 3. Very cool. Please note that it doesn't work to just add the number 4 without these braces here. That's an error, because that's the difference between adding 4 to a list and concatenating a list containing 4 to the list. Remember that plus, when we're talking about data structures, is a concatenation operator, not an addition operator. So, in order to add something to the end of the list, that's how you do it. This is also known as an appending operation. It's an extremely, extremely useful thing to know how to do for many of the assignments. So I would recommend practicing, trying it out yourself, understanding how it works. So, in the same way that we had list slicing operations for strings and tuples, the exact same list slicing operations apply to lists with the exact same rules. So if you wanted to rotate, or if you wanted to do the reverse of a list, that's how you would do it. If you wanted to get from, 1 to 3, there you go, etc., etc. So, again, plus is concatenation. We can take the length of the string with len. We have a test for membership in the string. We have the search operator in. So 2 in x, true. 5 in x, false. 5 not in x, correct. If you want to repeat the list, you use multiplication by an integer. So x times 8, there you go. The list repeated 8 times. And and if you want to count occurrences of something in the list or find the index of something in the list, which, if you remember, we already talked about these operators within the context of strings, so, you know, they are here too. So these are operations that we would call non-mutating operations. So if you'll notice, when I perform a slice, for example, when I performed the slice 1 to 3, the actual data structure X itself did not change. It did not mutate. It was not affected by the operation. In fact, what is happening is a new piece of memory is allocated, and the result of the operation is stored in that memory, and if you want, you can grab that memory by assigning it to another variable. So y would be the result of that operation, but x is unchanged, right? So that's the basic quality of non-mutating operations. However, because we're now working with mutable data structures, we now have mutating operations as well as non-mutating operations. So if we wish to add something to the end of the list x, we can use x.append some element 7. You can see that the list that is designated by the variable x has actually changed. Whereas if you were to do x plus 7, you get the 7 added, but again, the actual data structure x itself hasn't changed. That's because concatenation generates a new data structure. It is non-mutating. Whereas, if you use the append method, it does change the data structure. If you want an equivalent of a concatenation operator that is also a mutating operator, you have extend. So the x gets extended with the list 5, 6, 7, 8, which looks very much like a concatenation operator, except the modification is in place. X itself is modified. A new version is not generated. We can also insert elements into x, so x.insert at index for the value table. There we go. It has been inserted between the 4 and the 7 at index 0, 1, 2, 3, 4. There you go. We can also remove elements from the list. Remove at index 4, and you can see that 4 is actually removed. Interesting. Well, that's actually an error in the slides. So when you remove, it's actually searching for the element itself, not the index. That's interesting. That's an error in the slides. Well, there you go. You heard it here first, folks. You can also pop, so you can return an element at index I and remove it. And you can also reverse the list. Although, again, reverse. So the difference between reverse and ::(-1) is, of course, ::(-1) does not modify x itself. It just performs a calculation, stores it elsewhere, and you can grab that if you want. Cool. Now you know what it means. Yeah, that's interesting. I haven't had anybody, like, that penalty has not been meted out to anybody since back in the day before we made these live streams unlisted, and we had internet randos trying to junk up the chat with their ridiculous junk. So so let's all take a breath, because we're about to talk about something that's a little bit on the difficult side, but it gets into all of this business I've been talking about with respect to mutating versus non-mutating operators. So it's difficult to talk about this without introducing the idea of memory addresses, right? So X is not the list itself. The list itself is memory. X is a memory address. X is it's a number that indicates another area of memory, right? So if we can expose this in the same way we exposed the ordinals of characters, right? So this is the actual memory address at which this this piece of memory is stored, right? So if I perform a non-mutating operation, like say a reverse, and store that in Y is the reverse. If I take a look at what the actual memory address of Y is, you will note that these are different addresses, right? These are X and Y are stored in different areas of memory, right? So the difference between a mutating operation and a mutable data structure and a non-mutable data structure is you have some level of access to these addresses themselves. So this is, again, a little bit esoteric, but let's say I assigned Z to X, right? When I ask for Z, I get the list, right? If I make a modification to X, like that, yeah, I've replaced this 7 with 10,000. If I take a look at Z, oh look, that modification was also made to Z. Z is what we call an alias of X. What's actually going on here is that I've taken the memory address that X. So if X is a box, it has the memory address in it for this data structure. When I assigned Z the value that X has, I was not assigning it the data structure. I was assigning it the memory address. So that means that we now have two boxes, X and Z, which both have the same memory address in them, right? They both point to the same piece of memory. That means if you access and modify that memory through one of them, then you are also accessing and modifying it through the other one. The changes by one way will show up in the other way because they're both accessing the same memory cells because they both have the same address. And we can demonstrate that if we remember this. So that's the memory address for X. This is the memory address for Z. Notice that they are the precise same number, right? So this is, okay, so why are you telling me this? This seems like extraneous information that should only be interesting if you're taking a C programming class. Well, it has implications. This is mapped to the basic assignment operation, right? So the difference here, remember how Python passes arguments into functions. It uses pass by assignment. That means that when you pass a list into a function, any modifications that are made to that argument inside of the function will show up outside of the function. So, let's define a quick function. Add 3 to something x. X.append 3. Sure. So x. Let's just clear x. Let's do L. Is L? L's okay. So we'll use L. So L, add 3. Oh, actually, you know what? I'm gonna print it while we're in that function. Print x. X.append 3. So if I I want to do one more thing with it. Print, and then return it as well. So if I print add 3L, right? It prints it before. That's the print statement here. And I'm printing the result, so when I'm returning x, I'm getting this, right? However, if I take a look at L, L has been permanently modified by this operation that's going on inside of the function. Even though the append operation is occurring on x, right? Although the append operation is being performed on the formal parameter of the function, the actual parameter of the function is still being modified. This is not something that happens with integers. This is not something that happens with floats. This happens only with mutable data structures. And if you don't know that this is happening, you might be caught by it at some point. So this is another one of the reasons for this sort of general heuristic that we take, that you should try to avoid modifying arguments, because you're not sure. You can never, well, if you're really good, you can always be sure. But, you might be modifying more than you think you are. If you're not 100,000% confident in what you're doing, you might be modifying more than you think you are when you're performing that sort of operation. Cool. Let me see what chat's doing. So, oh my goodness. Come on. So, yeah, I just explained that. So what's interesting is you can even put these memory addresses inside of lists themselves. So if we have x, z, x, there we go. If I have a new list, call it q, 1, z, x, 3, this list, x, shows up inside of this other list. But, of course, it only looks that way because that's how it's being printed, right? Inside of here, that's actually, once again, an alias. So if we modify x again, so say x.append, yep, the modification shows up inside of Q as well. Aliases. So this is a sequence of operations, and we have to determine at the end what the value of E is. So we create a list 1, 2, 3. We create an alias for that list called B. We create a new list, C, which contains 4, 3, and an alias of B. We then assign the first element of A to the second element of C, so 1 becomes 5. D is then assigned the third element of C, which is B. So D becomes an alias of B, and B is an alias of A, and A has been modified, right, to have the value 5. So when we get, so E, when we ask for D at 0, D is an alias of B, which is an alias of A. A at 0 is has been assigned to 5, so the correct answer here is 5. Ta-da! So that's like a contrived example. You won't see anything like that on a test probably, but you know, aliasing is an important thing to know how it works, just so you don't get caught by it primarily. So, slicing. So we've already talked about slicing a fair bit, but let's just pardon me. Let's recapitulate it a little bit. So we have a string x, right? Or, you know, we'll do these examples here. Already talked about this a lot, but so just to make everything perfectly plain, if you have no colons, that means that the indexing operation has one argument. That argument will always be the element, the sort of n+1th element of the data structure. If you have a colon, that means that you are looking for two arguments. The first argument and the second argument. If you leave the first one blank, you mean from the beginning of the string, or from the beginning of the data structure. If you leave the second one blank, that means to the end of the data structure. So, blank colon blank is actually a great way to duplicate data, because this sort of it actually, so this is actually your sort of quick and dirty way to break an alias. So if you want to create a duplicate version of a data structure, so say x, instead of doing, you know, f is equal to x, because you know, f will just be a alias, right? Hex ID x, hex ID f, they're the same thing. If instead you say g is equal to x blank colon blank, g has the same things in it as x. However, if you take a look at the memory address, you'll note that the memory address has changed, because we have essentially used a non-mutating operator that does nothing. So that ends up being a data duplication operation. So, if you were to modify g at 3 is equal to something, g has been modified, x has not been, because that link has been broken. Cool. But anyway, back to slicing. So, when it's not blank, you're selecting the starting point of the slice. When it's not blank, for the first argument. For the first argument, if you put a number in there, that's the starting point of the slice. And if you don't leave the second argument blank, that's the ending point of the slice exclusive. So it will stop one before that. There you go. If you include a third argument, that's how many you want to count by. So if you count by 2s, you take every other element. If you count by 3s, you take every third element. If you count by nothing, or you count by 1, that's just the slice itself without any skipping. And if you count by negative ones, that doesn't work unless you have, you know, unless you have left the other two blank, in which case it's a reversing operation. So there you go, slicing. I'm going to skip the rapid-fire quiz slide because this is online and that doesn't really work. So yeah. Yeah, you can also use copy. Sure. But, you know, if you want to get fancy about it. Bracket colon bracket is less characters, though. Was that a delivery van? Not for me. Okay. So, in summary, tuples are like lists, but they are immutable. Tuples do not have aliasing, and they are faster. So that's another case where you might prefer to use a tuple over a list, is a situation where you want to avoid aliasing entirely. Whereas lists are slower, but they allow aliasing and they allow assignment to their elements. Cool. Are there any questions before we move on? Yeah, this is kind of getting into this business I was talking about how there's 100 million ways to do anything in programming, despite the fact that it's an explicit design philosophy of Python to reduce the number of redundant ways of doing things. You still get this effect where there's just 100 million ways to do anything. So, having talked about lists, let's talk about sets. So, sets. When we are talking about sets, in Python, the theoretical basis for sets in Python is sets in mathematics. So, you know, Frankel-Zermelo set theory, essentially. It's not as basic or, you know, fundamental as set theory in mathematics. For those of you who are not aware, set theory in mathematics is one of the most fundamental levels of mathematics that have ever been developed. That is to say, set theory is a mathematics that's capable of expressing, I believe, most, if not all, other forms and branches of mathematics, or at least the, you know, the more common ones. Mathematicians in the crowd will be able to correct me. So it's useful to be able to deal with sets of things. So what is a set, mathematically defined? A set is a collection it's an unordered collection, right? So the thing about something like the natural numbers, that is technically a set of numbers, but there is an ordering that's imposed over it. So it's sort of a set with an ordering property. The normal analogy that's used for sets in mathematics is if you think about a bag full of marbles, where each marble in the bag is a unique marble. That's sort of the idea of a set. So in Python, we are very stringent about this idea that sets must exist without repetition. In sort of the formal mathematical sense, I'm not sure that that's a strict property of sets. I think that might be... that is to say, I don't think that's a property of all sets. However, it is a property that can be applied to sets. So, you know, for all x and y elements of set S, x does not equal y. That's a property. So, if you have a set... So, some examples of sets. The colors are a set. The set of even numbers less than 10 is a set. Sets. Yeah. So, in mathematics, we have set operations as well. So, let me just pull up set operations. Oh, they want me to restart the thing that I'm live streaming on. That's probably not going to happen. Woo. No, thank you. I'll use Opera. Set union. Yeah. Set operations. Images. Yes, here it is. So this is specifically about Python, but this is true of set theory in mathematics, not just Python. So we have a few operations. We have union, intersection, difference, and cardinality. Union means everything that's in set A and everything that's in set B. But because because we're not allowing duplication, it's like it's sort of in terms. It's easiest to describe this in terms of Venn diagrams. So union is everything that's in B and everything that's in A and everything that's in B. So, you know, sort of both sides and the middle of the Venn diagram. When you're talking about intersection, you are talking about only those elements which are both in A and in B. So in terms, like if you were to compare this to Booleans, this is similar to an OR operation. This is similar to an AND operation. Difference is all of those elements in A that are not in B, so we exclude the middle. And cardinality is the number of distinct elements in A, so, you know, essentially equivalent to our length operation. So, if we want to create a set S, we use round braces. So, if we have some number of elements in a set can only contain unique elements. So if we ask it to show us what the elements in the set are, you can see that all of these redundant 5s and 2s and 7s, etc., have been eliminated from the set. They are gonzo. The set that remains is only those elements that are not that are unique. So let's say we had A as 1, 2, 3, 4, and B as 3, 4, 5, 6. A bar B is the union. So that's all of the elements that are in A and all of the elements that are in B without repetition. Ampersand B is the intersection. So you can see these, you'll see in other programming languages, bar and ampersand are used for OR and Boolean operations, respectively. So you can see where that sort of analogy is coming through. So the only elements that are common to both A and B are 3 and 4. So those are the ones that remain in the set, or are a part of the resultant set. The difference, S subtract T, you can think of it. Sorry. A subtract B are all those elements that are in A that are not in B. 3 and 4 are in B, so they are not included in the result. Ta-ra! And length of A is 4, because that's the number of things in it. We also have a test for membership. The same test of membership that we are used to by now also works over sets. And if you want to designate an empty set, you do not use empty curly braces. That denotes an empty dictionary, which should show you how much more dictionaries are used than sets. But if you set with empty braces, that is an empty set. So there you go. Set operations. We also have some operations that perform modifications over the sets. you may notice these look very similar to the mutating operations that are applied to lists, so we may conclude that sets are in fact mutable data structures. So if we have A and we want to add an element E to it, we use dot add, and it works. If we wish to remove an element, we do discard a dot discard some element, and that gets rid of it. And if you wish to return and remove an arbitrary element, you do a dot pop. That removes it and returns it, right, in one step. So it's not super important, but the statement arbitrary here, it's important to note that the elements of a set, there is no ordering over the elements of a set. The reason that the pop operation is arbitrary is because you cannot assume that the elements of a set are in any particular order, not even the order with which they were created. So it's sort of a little bit facile in this example, because we're doing 1, 2, 3, that contained sort of maybe a mix of things. Notice when I print this, the elements end up in a different order. So it just so happens in Python, printed in is the order that they will be popped in. But normally, when you're writing an algorithm, you can't just stop writing the algorithm and check. You don't know what the input will be, so you can't just you can't. Okay. Wow, that's terrible compression. Okay, so... Okay, guys. I'm gonna call... I'm going to just take... I'm just gonna take this... take the next 10 minutes. I think I'm just gonna check my router, see what's going on there. Because... Look... Hello. We're back. Hypothetically speaking. I do not know what caused that problem. I am not sure. I'm just waiting to see if my voice is coming through, and hopefully everything is good. Seems like we... Oh, there we go. That might help for me not to be 2 minutes behind. I think I'm using the wrong... Test. Yeah, I think that's good. Since I changed the USB ports, the camera problem hasn't reoccurred, so maybe that actually fixed it. Fingers crossed. Fix one problem, you get another. That's life. Am I right, guys? Oh boy. So, it is possible to compute the unique elements in a list or a set, or a list, pardon me. It is possible to compute the unique elements in a set by using sorry. It is possible to compute the unique elements in a general collection by using sets. So def unique something L. If we set up S as an empty set, for each element in the data collection, S is equal to S union, the element of that collection, all by its own, and then return the length of that set, then we get the number of unique elements. So, for example, if L is, again, one of these lovely randomly generated number sets, print unique L, Python 3. So the number of unique elements is 12. Ta-ra! There's actually a much shorter way of doing this even, which is kind of cool. Def unique to L. You can just return the length of the set conversion of L, and that does the exact same thing. Bing! Ta-da! You can also use in situ insertion rather than reassignment with the union of the set and the individual elements. So there you go. Gonna skip the rapid fire round again. So in summary, we have tuples, lists, and sets so far. Tuples use round braces. Lists use square braces. Sets use curly braces. In tuples and lists, you are allowed duplicates. In sets, you are not. In tuples and lists, ordering is permitted. In sets, the ordering is arbitrary. And in tuples, things are immutable. In lists and sets, things are mutable. So there you go. So, having covered sets, there we go. Let's move on to the other super useful data type, which is dictionaries. Dictionaries are something that you'll see. It's like, in terms of usedness, it's probably something like lists, strings, dictionaries, tuples, sets, if I were to rank order them. So, lists, strings, and tuples are all integer indexed. So these are linear data structures. Dictionaries, by contrast, are indexed with arbitrary types. So this is cool. Rather than have things occur in a linear arrangement, with a dictionary, you decide what the indexes are. So if you wanted to say apple 3, orange 7, avocado 15, dictionary at apple is 3, dictionary at avocado is 15. So rather than, instead of just this being like a linear arrangement, you can actually create what's called a mapping between two different pieces of data, right? So you can see how conceptually this is like, this can be a very useful tool. So the caveat of that, of course, is that you lose access to accessing the elements of a dictionary by number, right? You can't access the elements of a dictionary by number unless the numbers are the, unless you put the numbers in the dictionary as things you can look things up by, which is totally possible, totally permitted. And the oop, what have I done? I crashed that tab for somehow. Anyway, so unless you have explicitly designated, you know, the integers 0 through whatever to be the keys of the dictionary, they're not going to be, it's not accessible that way. So here's a quick example of how this might be useful. Let's say you wanted to tell a computer how many days there are in each of the months. Days in month: January 31, February 28, March 31, April 30th, etc., etc., etc. Then you can access, you can get the number of days in the month by referring to the abbreviation of that month name itself as a string. So that's cool. So dictionaries, so this is a bit of important nomenclature. Dictionaries contain what are called key-value pairs. So the thing that you get to the data using is called a key. Think lock and key, right? The dictionary is like a locker room, and each of the lockers is opened by a specific key. In this case, the keys are things like, you know, strings and integers and other literals, right? The data contained within those lockers, those are the values, right? So the key is the thing that opens the locker, and the value is the thing that's in it. Cool. So the way that you create a dictionary is, man, I wish that tab hadn't crashed. There we go. We'll just open up a new one. Create a new one very quickly. So the way that you create a dictionary, the way that you add things into a dictionary upon creation, is you have a comma-delimited or comma-separated list of a key and a value separated by a colon, all of that enclosed in curly braces. You can also create blank dictionaries, blank or empty dictionaries, using empty curly braces. The fact that dictionaries are used much, much, much more commonly than sets is the reason that empty curly braces denote an empty dictionary and not an empty set. So rather than thinking of it as an indexing operation, with a dictionary you should think of it more as a lookup operation. So we look up the value at A, we look up the value at B. We also have a test for membership, but the test of membership looks at the keys, not the values. So that's a bit of a difference. So, you know, 3 in dictionary is false, but C in dictionary is true. It's looking at the keys. If you want to delete a key from the dictionary, you delete C, D at C. Oh, dictionary, sorry. And then the dictionary no longer contains it. If you want to get the number of things in the dictionary, the number of key-value pairs in the dictionary, you use our ever-present, ever-helpful length operator. And if you want just the keys, if you want to separate out the keys from the values, there are dict.keys, dictionary.keys, which gives you just the keys of the dictionary, and dictionary.values, values, which gives you just the values that are in the dictionary. So if, for example, you wanted to search the values of the that are in the dictionary rather than the keys, you could do something real quick, like 2 in dict.values. And that comes out true, because this thing is searchable. Ta-ra. There we go. Yes. So one of the interesting things about dictionaries is many keys can have the same value, but the keys themselves have to be unique. Really, thinking about it as like a bank of lockers in a locker room is correct. When you're making lockers in a locker room, you don't make it so that every locker is opened by the same key. Otherwise, you don't know where you don't know which locker is yours. The key doesn't specify a locker. Whereas, if everybody's, it's totally completely possible for everybody's locker to compare, a half-used stick of deodorant and gym shorts. Although it's kind of like, in the same way that each locker would contain a different half-used stick of deodorant and gym shorts, they would be separate instances of a half-used stick of deodorant and gym shorts. The same thing would apply in the computing context, unless all of those things were aliases for some other data structure somewhere else in memory. So there you go. So, dictionaries are mutable. Mutable. So, dict A is equal to 7, modifies the value. And an interesting thing is, if you want to add something new to the dictionary, all you have to do is assign to a new key. So you can add things to the dictionary with just simple assignment operations, which is kind of fun. Very cool. Useful. Let me see if there are any questions. So yeah, a key has to be something with a literal, right? The keys have to be literals. Although, well, actually, let me see. Maybe we could do something like, often you can do more than you think you can. No, yeah, tuples can totally be keys. There you go. Tuples can be keys, folks. Probably the rule is anything for which an equality operation has been defined is a valid key. So, you could, if if t is equal to 1, 2, 2, 3, and t is equal, testing equality, is t equal to 1, 2, 3, that comes out true. So equality comparisons are valid operations over tuples, so that means that when the dictionary is looking for the key, it has something that it can use to equate, the thing, the index you give it with the key that's in the dictionary. So, let's talk histograms. Histogram. Ah, so lists don't work then. Okay. I'm going to test your theory, Mark. So dictionary 456 equals some number. Haha, unhashable type list. Okay, there you go. So lists cannot be used as the keys of dictionaries, but tuples can. And that would make sense, right? Because tuples and strings are, very, very similar, and strings can be used for the keys. So, you know, why not tuples? Hashtag why not tuples? Yeah, so histogram. So a histogram, if you remember statistics, determines the frequency of items in a collection. So let us create a function that creates a histogram. So def hist takes some collection C. So basically what we want to do is we want to create a dictionary which tracks the frequency of the elements of the collection C. So in order to do that, we should start off with an empty dictionary. So say output is equal to an empty dictionary. For element in the collection, out at element plus equals 1, return out. Let's say collection is equal, let's just use a string. Hello, my friends. Welcome to Meat Land. Like a theme park. Histogram on that. Let's call it S for string. Print the results. Let's see what this does. There are some pretty weird theme parks out there. Key error H. So I've made a mistake. I actually made this mistake intentionally. So, key error. We hit the first letter here. We try to add 1 to the element, right? But it's not in the dictionary, right? Let's in fact display the dictionary at each step, see what things look like. So it's empty. We are looking to increment whatever is at key H. Key H doesn't exist, so it flunks out on an error. So the solution to this is we have to test. If E is in out, then we can do that. But if not, we have to add it. Out at E is equal to 1. Ta-da! It's not working, though. Still. Oh, I did out at 3 and not out at E. What a stupid thing to do. There we go. So, let's just minimize the clutter here. So, we've got H-E-L-L-O, 4 L's, 5 E's, 3 O's. Yeah, so there you go. That's a histogram. Cool, right? Yeah. So, the other interesting thing that the other tool that we have on our toolbox when dealing with dictionaries, you can use for loops with them. When you use a for loop over a dictionary, rather than doing the value or the key value pair, the for loop will assign to the variable the key. It'll go through each key in the dictionary and do the loop once for each key. So, for example, we have this dictionary. For k in dict, print k. This is essentially equivalent to the keys function, right? Except it's like the keys method, and then you also used a for loop in the same instance. If you want the values, of course, all you have to do is use dictionary lookup, and there are your values. Super, super, super simple. So, this is another rapid fire round. Which data type would be most appropriate for the various for the following different applications? So, 5 nominees for best animated film. These would be strings because they are names of films. You know. Well, I don't know. Perhaps this is just going to be a lot of me talking about unrelated stuff, so perhaps this is best left as an exercise to the reader, I think. Yeah, I think so. So, let's just move along to the problem-solving angle, then. Cool. Let me see if there are any questions about that. Oh, Mark's on top of things. So we're gonna talk now about a particular problem called the make-change problem. This is a well-understood problem within the space of algorithms research, or at least it's a subclass. It's a particular instance of a subclass of a very thoroughly researched type of algorithm. So here's the problem. Let's imagine that we are not living in COVID times, and we are actually at an actual store, and we wish to purchase a soda pop. We get up to the counter, we hand the cashier however much money, and the cashier has to make change for us. In general, the goal of the cashier will be to give you change in as few bills or coins as possible, right? The cashier is not going to give you your change exclusively in nickels, because that would be ridiculous, and you would say, "Excuse me, you have given me my change all in nickels, what gives?" So, in general, every cashier that has to actually give someone physical change, ever in the history of cashiers, has used some version of this algorithm in order to do that. So, in particular, let's consider the Canadian coin denominations 5, 10, 25, 100, and 200 cent coins. So nickel, dime, quarter, loonie, and toonie, respectively. And a target amount of change, 185 cents. So, if we were to do this out on paper, almost paper, quasi-paper, virtual paper, our target amount is 185. Obviously, there are no toonies that we can give out, because even the smallest, like a toonie, is bigger than that element, that amount, so you can't give any toonies. 1 loonie would fit in there. We subtract that total, so we're left with 85. 3 quarters would fit inside of that. That would be 75, so we are remaining 10 cents. Then we just give the rest as a dime, and then that's done. Our solution to this problem is 131. However, this is not a unique solution, right? You could just as easily have done 2 nickels. You could do the whole thing in nickels if you wanted to. So the idea is that this is a math problem that has a field of solutions, one of which might be optimal, right? So in algorithms research, you have these types of problems where, you know, there are many different answers that would, that would satisfy the conditions of correctness, right? There are many different solutions to this problem that would satisfy adding up to 185. However, so in that case, we add the additional constraint that we want to find the solution to the problem that minimizes the total number of coins, right? The total number of coins should be the smallest of any solution. Fine. So let's first write an algorithm that computes that computes the answer along the way along the lines that we just did, which is sort of your intuitive manner of solving this problem. If it's not your intuitive manner, then I apologize. It's slightly subjective. But let's write an algorithm for the make change problem. So first, of course, before we write the algorithm, we have to know what the inputs are and what the outputs are, right? In the same way, when you're solving an assignment question, if you've attempted any of them yet, the assignment questions are specified in terms of input and output, right? We tell you what the inputs should be, you tell us what the outputs should be. So in this case, we are taking two inputs. We are taking a tuple of coins with their denominations as integers, and we are taking a target value as an integer. So we can already write our define statement, our function initialization. So def make change takes a tuple of denominations and some target value. Our output will be a dictionary where the keys are coin denominations and the values are ints corresponding to the number of coins of each denomination. So we know that we are outputting a dictionary. So return quantity, or just call it D. Capital D will do. So how do we approach this problem? Well, we know that we want a dictionary at the end that has as its keys all of the elements of the denominations tuple, right? So we can actually set that up ahead of time. One of the very, 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 very important things that you have to do when you're designing an algorithm is you have to take the problem, break it into chunks, solve those chunks individually, and then smash the solution back together again. This is known as the principle of decomposition. It ties into the idea of modularity. It's an extremely important principle in software design. The ability to break a problem into smaller, manageable chunks, solve those individually, and recompose the answer from the solutions to those smaller chunks. So, task number 1. We must create a dictionary with keys that are the denomination values. So, quite easily done. Set D as an empty dictionary. For coin in denom, D at coin is equal to 0, because we haven't decided how many are in each one yet. There we go. We can then print D, see what we get. And I'll just write in a quick test case. Make change. Let's use the one in the slides. So 5, 10, 25, 100, 200, and with a target value of 185. And print that. Sure. So, there we go. A dictionary with the keys as the elements of this tuple. Task 1 accomplished. Ta-da! Yes. So now we need to run through that algorithm that we were using to compute how many of each coin we want. So we need to start with the largest coin and move down to the smallest coin and decide if our target value is greater than or less than the coin we're currently working with. So for that, we will need a loop. But we may wish to configure our data so that our numbers are in the correct order before we get there. So, let's say coin values is equal to denomination list interpretation of denomination dot copy. Maybe this will work. Nope. All right. I think that'll just work. Good. I'm gonna print this. Right. Now we want to sort it. Coin values dot sort. It's already sorted. And since that sorts it in ascending order and we need it in descending order, you just reverse it. Or you can actually use the dot reverse method. That would work as well. So there you go. Now it doesn't matter what order these guys are in. The algorithm will still work because we are rather than relying on the user to provide the coins in a particular order, we are taking the data and turning it around and turning it into what we need it to be inside of the function itself. A more highly mathematical way of putting this is that we are removing preconditions from the function. We don't have to make as many statements about what the input needs to look like. We can now accept more general lists of things because we do a little bit of this. I would consider this to be pre-processing. So our coin values list is now in the order that we want it in, so we can just for loop over it. So for coin in coin values, we now get to the math. So our algorithm in general was we took our coin value, we examined, let me just reconstitute that, we examined to whether this coin value was greater than or less than this guy, right? So that's easy enough to do right there. If coin is greater than the value, the target value, then you do something. Otherwise, you do something else. So when the coin value is bigger than the target value, we actually don't want to do anything, right? So it would actually be more to the point to make this a less than and drop the else case. Cool. When the coin value is less than this element, what we want to do is we want to see how many times we can fit this guy into this guy, right? The quarter, for instance, fit inside of 85 3 times. So we need to know how many times. And you can do that a couple of ways. You can either do that with a loop by counting it out, or you can use division, because that's what division is for. So print val integer divide by coin, and we'll just see what that looks like. So in the case of this guy, 100, we get 1. That's correct, actually. The rest of the results, because we're not modifying the value as we're going down, we're not getting correct results here, but suffice to say 37 quarters, or 37 nickels would fit inside the target value in this case. The other thing that we want is we want to know how much would be left over once we take out all of the loonies from this amount, right? And we happen to have an operator that does that too. It's called modulus. So val mod coin. So we fit 1 loonie and have 85 cents left over. That's correct, actually. So we want the running value to become that remainder value. And we want the number of coins that fit in there to be added to the dictionary. So d at coin is equal to that. So let's see what happens. Well, we get 100, 3 25s, but 10 is being skipped for some reason. Also, where is our... our print statements were gone. Less than or equal to. That's the trick. So, see how less than or equal to can mess you up? So, if the amount that's remaining is exactly equal to the coin value, then we just have 1 left, right? And that's good. That's fine. We actually want that. So, yeah, there we go. Once we make that change, we get the correct answer, which is 1 loonie, 3 quarters, and a dime. Ta-ra. So there you go. This algorithm makes change. Cool. Let's see how we did in comparison to the slides. Well, all right. Boink. Boink. Why isn't it? It's not auto-side. That's annoying. Jeez. All right. There we go. So let's see how we did. Oh, analysis. I'll come back to that slide. So, in this guy, first of all, they're using a while loop rather than a for loop. But that's because they're counting down, right? Like, the thing about a for loop is it only counts from beginning to end, right? So we had to perform this reversing operation in order to get the biggest things at the front and the smallest things at the end, because that's the order in which we need it for this algorithm. If you use a while loop, you can just start at the end and go forward. So it doesn't, it's a little bit more flexible. But, also, consequently, if you forget this minus equals 1 step, then you end up in an infinite loop, which is not going to do you any good. So, the only difference here is that first of all, we have num of this coin as a redundant expression, because you can just easily pop that here. And they're using target minus equals the coin value times the number of the coin instead of using modulus. But otherwise, this is precisely the same algorithms as we were using before. Cool. So the procedure that we're talking about here is something which is called a greedy algorithm. The reason that we call it a greedy algorithm is it takes the first solution it finds. Remember that I said when we find solutions to this problem, there are a few of them to find, right? There are many different solutions to this problem that we can evaluate for how, like, by some secondary criteria. In, like, again, it's formulate 185 cents out of exclusively nickels, but we consider that to be a suboptimal solution because nobody wants that many nickels, right? But the idea that nobody wants that many nickels is a secondary means of an evaluation that we are layering on top of, technically and mathematically speaking, correct, right? We are placing an additional mathematical constraint on it. So what the greedy algorithm is doing is essentially ignoring that secondary constraint. It's not going for the most immediately simple algorithm. Like, the simplest algorithm here would be to just return everything in nickels, assuming everything was divisible by 5. But it picks a particular method of analysis, and it just goes with it, and it does not evaluate. It doesn't do it in several ways and compare them. It's just like, I'm doing it this way. I'm gonna pick the first solution I find, and that's gonna be my solution. Greedy algorithm. Cool. So, as you might imagine, you don't necessarily end up with a solution. So consider the following case. What if we have a coin set 1, 5, 7, 10? I know this is not necessarily a coin set that actually exists, although I was a couple of years ago, my wife and I went to Spain on our honeymoon, and I was surprised when I had to interact with the coins, the euros, the euro coins, because they have like so many different coins. It's like they've got 1 cent, 2 cent, 5 cent, 20 cent, 25 cent, 50 cent. Like, there's just like so many different euro coins. It's amazing. So this isn't as far-fetched as you might think. But anyway, let's consider this example. We have coins 1, 5, 7, and 10, and we're trying to hit the target value 14. What are we going to get? We get 4 1-cent coins and 1 10-cent coin, because it's going from the biggest to the smallest. However, that's not the optimal result. The optimal result would be to say you get 2 7-cent coins. So in order to find that, so this kind of gets into the idea that the make-change problem is what you would call a hard problem. It's in fact a NP hard problem. So NP stands for non-polynomial. Because we cannot employ a straightforward, loop-based algorithm to guarantee the, most correct result in this case, we require something a little more fancy. We might require something like a dynamic programming solution. Basically what we need is the ability to test out different hypotheses about what the correct result is, and then eliminate those which result in suboptimal solutions, right? That vastly increases the number of tests that you have to, execution time that it takes to perform the algorithm. It turns out that it actually inflates the execution time quite substantially. Non-polynomial algorithms are called non-polynomial algorithms because the amount of time they take to run is proportional often to the 2 to the power of the number of inputs, or something like that. We're gonna talk about this when we talk about big O notation relatively shortly in this class. But so this is kind of like a soft introduction to it. But essentially, how certain types of problems work is it's actually extremely difficult for you to check every single possible value of input, right? That's a thing that is actually, technically speaking, impossible. Though not theoretically impossible, it is practically impossible. So let's imagine let's imagine that you were running Twitter and you wanted to check every single possible tweet for some combination of characters, right? Let's say you wanted to I don't know. It doesn't matter. You want to check every single tweet, right? Every possible tweet. That means you want to check every possible arrangement of 140 characters, right? So every character, even if we assume that, we're dealing exclusively with ASCII, right? Google. So 128 possible characters, right? Multiplied by the number of characters in a tweet, right? So 140. So we have 17,920 there, right? Each one of these characters is a unique arrangement of bits, right? So the number of possibilities here is actually 2 to the power of that. Oh, no. Yeah, no. Sorry. I messed it up. Assuming each character is 8 bits, right? What we're trying to do is we're trying to measure the number of bits of input. This is just a simple mathematical demonstration. But, yeah. We might be able to do it in the Python interpreter, actually. So, 2 to the power of the number of characters multiplied by the number of bits per character. So let's say, very generously, 8 bits per character, right? So this number represents the number of possible tweets that exist, assuming an extremely restricted character set, right? That's a big number, right? Like, we're in territory of, like, if every atom in the universe had another atom in it, or if every atom in the universe had another universe in it, and every atom in that universe had a universe in it, and every atom in that universe had a universe in it, and every atom in that universe had a single number on it, like, that's the sorts of orders of... You're probably still off by quite a substantial degree. Another way of saying this is, if we assume that we can process 1 million of these per second, right? Integer too large for a float. Okay. Oop, can't even perform that math. It would take longer than the universe is old to go through every possible input there, right? So things blow up extremely quickly, and this contributes to the problem. Basically, whenever you start running into those types of issues, you're in NP hard territory, right? So let me see. There are algorithmic approaches to attempting to solve NP hard problems efficiently, but there's actually no, like, general solution that makes all NP hard problems easy. It's actually it's kind of like it's the white whale of computing research, right? It's like the thing that everybody shakes their spear at because it's the unsolvable problem. If you solved the NP hard problem, if you proved somehow that NP hard algorithms could be done in polynomial time, what you would effectively do, well, first of all, you would become the richest, most famous person on the planet within within the limitations of how famous a scientist can be. And you would also break all existing encryption, because encryption relies on this like vast multiplicity of possible states in order to work, right? The reason that you have a password and that passwords work is because the number of possible passwords is extremely large. So to guess any particular password is extremely difficult. This is the same reason why serial numbers on gift cards are an effective system for making sure nobody else gets your gift card money, right? Because it's virtually impossible for someone to guess a gift card number that's valid, right? Because it's kind of like you have this vast space of possible gift card numbers, and only a vanishingly small number of actual gift card numbers within that space correspond to actual money, as registered in some server somewhere. So that's why encryption works, right? That's why codes work. That's why passwords work. That's why serial numbers work. This is why, because it's virtually impossible to exhaustively test the space of anything even reasonably sized. And this should give you some clues as to how to set up your passwords so that they aren't easily guessed by people. The more characters there are in your password, the more possibilities. Each additional character that you add to your password adds like 2 to the power of 16 possible. It raises the number of possible passwords by a power of 16, right? So if you it's like 2 to the power of 16 times the number of characters in your password. So that's the number of possible 8-character passwords. That's the number of possible 16-character passwords. Hiding 1 inside of this number is pretty good. Hiding 1 inside of this number, that's much better, right? So, some of the most, so if you have like a ridiculous 90-character password, you can see the number, the longer your password is, the more secure it is, basically. And, aside from that, it's also don't use commonly used passwords, obviously. And the reason that password, when you're picking a password, they sort of force you to use special characters and numbers is because, if all you're using is the if all you're using is the alphabetic keys, that's 24 times 2 possibilities, right? But if you expand that by, just the numbers 0 through 9, that increases the number of possible passwords very, very, by a very large degree just by adding, 10 more characters. If you throw all of the symbols on top of that, you have, you've vastly increased the number of possible passwords that hackers would have to get through, because, in order to guess your password, people use heuristics, kind of similarly to how the greedy algorithm uses a heuristic to simplify the coin making, the make-change problem. When a hacker is trying to guess your password, they're making some assumptions that are common among people, right? People, generally speaking, will, they will use a word in their password, like an English word. If you have a list of English words, that's, there's maybe 5,000 English words or something. Or, maybe 10,000, whatever. It's very, the number of English words is very, very small in comparison to the number of possible passwords. Even if you use 2 English words, that increases it, but it's still very restrictive, right? So, you know, yeah, anyway. Guess I was on a bit of a rant. But anyway, so that's we'll talk a little bit more about what it means for something to be NP hard. But yeah, I guess that's class today. We've come to the end of it. We're actually on schedule for once, which is nice. So yeah, I'll leave you here. You guys can get to your tutorials. If you have any questions, please put it in the chat, and I will respond to it. But otherwise, have an excellent Tuesday. You're welcome. Thoughts on quantum computing? I'd be more terrified if I thought that they could at any point be like miniaturized to the point of being available as consumer electronics. I don't think. I do not like. Quantum computing, in theory, can break all existing encryption because it can solve the NP hard problem by using quantum properties like superposition. In a quantum computer, a bit can represent can be in multiple states at once because of quantum effects, effectively. So, in theory, that can break all existing encryption. Well, it would be an extremely powerful tool in the information wars, assuming that such power was in the hands of people who were on your side of anything like that. Yeah. A malicious agent could certainly wreak havoc upon the world with such technology. So let's hope that it never falls into their hands. It's kind of like quantum computing is kind of like the atom bomb of cyberspace. Let's put it that way. That being said, it's very cool, you know, like nuclear fission is cool as a concept. I just wouldn't want to have it dropped on my house. And I kind of feel like the same way about quantum computing. Well, that seems to be everything for today, so I'll be signing off here. Keep it real, folks. Hopefully everything goes well. Have an excellent rest of your week, and don't stress out too much about Assignment 1 and 2 if you haven't started them just yet. They're easy. They're not bad at all. At least from the perspective of, you know, a person who's been doing programming for many years. So, if you don't find them easy, that's fine, because you're learning. But, you know, certainly Assignment 1 shouldn't be too difficult.